Hello. So one thing that we still didn't talk about till now is why we call it this whole module statistical machine learning, which is essentially interchangeable in this case with saying Bayesian machine learning. Um, so what's important to know here is that there is a bit of a philosophical difference between what's known as the classical or the frequentist view to probability and the Bayesian view to probability. And based on these differences, we have different ways that we actually estimate these probabilities. So today's lecture is actually going to be focused on understanding this, and it's actually going to be quite important to understand these differences because they are actually going to help us understand better why we're doing things in a certain way when we reach like future lectures, essentially. But before doing that, I thought to first just quickly cover what probability density functions are, as that's something we were not able to cover in the previous lecture when we started the whole idea behind probabilities. So here I'll just be finishing up on our discussion on probabilities. So this won't be very detailed. It's just more like a definition of what these are and why we need them. So let's consider like computing probabilities with respect to continuous variables, right? So it becomes difficult when we come into the continuous domain to start thinking about probability of having a very specific value. Um, so what's the probability that you after you know a certain event that happens, taking a specific continuous value. Um, it's That's something that we can't just express like this. So one thing we can do, instead of like looking at the probability of just the value of just some value x, right? We can express it more as probability of x lying in some interval x um, and x plus dx, right? So if we express things in this manner, then it becomes much easier for us by making use of what we call probability density functions. Um, so let me show you visually what I mean by this. So uh, let's assume we have something of this sort. So let me plot using the blue color here. So we have this function. We have this function that we call a probability density function, and we're represented by px. So px is certain attributes, properties rather, about it. So px is always greater than or equal to 0, right? And the integral between minus infinity and infinity of px dx is equal to 1, right? These are the properties that this function has. So because this function has these properties, we call it a probability density function. How do we come up with this? That's not important right now. Right now, you just need to know what it is. And later on, if we need to go more into depth, into the details of how we compute this in different scenarios, we'll do that. But for now, the definition is sufficient. So it has these properties, and now we can just compute some probability. So for instance, it becomes much more easier that when we have a function like this, and someone asks us what's the probability of this function lying between two certain values, right? So for instance, what's the probability that this function lies between so if we have here this being an a and this being a b, and then someone asked us what's the probability of this function lying between a and b. What we would do essentially is compute the integral between a and b of px dx, right? Essentially, that's what we need to do in order to actually, what you call this, compute the probability of this function lying in this interval. So when we start looking at statistical distributions, this will become much more clear to give us more context. Right now I'm just introducing some terminology behind this. So basically this is the idea, and this is just computing probability for continuous variables, but still the same rules of probability apply, which is the summation rule and the product rule. So that means if we want to compute px, right, we can do it by saying it's the integral of px comma y over dy, which is our sum rule. This still applies because we're summing over all possible values of y, so this is the marginal probability we're computing here, px. And if we want px comma y, using the product rule, we can express this as py given x times px, right? That's another thing we can do even in the continuous space. So where this is the product rule, so both the sum rule and the product rule still apply, even when we're talking about the continuous domain. I'm not going to go further than this right now. This should be sufficient to give you an idea of what probability density functions are. The next thing I'm going to briefly talk about is expectations, right? Again, this is just definition so that you know what they are and such, right? So when we refer to expectations, what we mean is the average value of some function under some probability distribution px, right? So if you want to know the average value of a function under some probability distribution, we call that the expectation of that function, right? So given some function, f of x, and we want to compute the expectation of this function, which we represent by expectation of f. So this is the average value of this function under some probability distribution, and we do that by summing over all possible values of x, px, f of x, right? This is essentially in the discrete case, and we can also just take the integral of px fx dx, right, in the continuous case. So essentially this should give us the expectation of that function. So this is not really limited to just one variable. Once we're dealing with multiple variables, let's say we'll want the expectation with respect to x of some function f(x, y), right? We can do this as well, and the output of this will actually be a function of y, right? So this is a function of y because when you take an expectation with respect to x, you assume that y is a constant. The same thing we can also express like expectations in the conditional case, like the conditional expectation of f given y, right? And this is essentially the summation over x of px given y times the function itself, right? So again, we're just extending definitions of things that we already know, like that we covered in probability in the previous lecture, and here we're just giving you the definition of these terms. That's essentially what I'm trying to do here, so you don't need to get fixated on all of this right now, but it's just good to know and understand what these things are anyway. And then we can also, of course, talk about the variance, right? That's another topic we can talk about, where we say the variance of a function is how much variability there is in that function around its mean, right? Its mean is essentially represented by the expectation of that function, right? So the variance of a function, oh, let me try this again. So the variance of some function f is essentially the expectation of that function squared, right, minus the expectation of that function squaring the expectation itself. Right, so there's a whole derivation of how we actually reach this formula and stuff like that, but again, I'm not going into this. It's not important for now. So yeah, that should basically cover this thing. Of course, there's also a notion of covariance, which is how to what you call this, how two variables x and y might vary together. That's another thing we can look at. And in the case of covariance, let's say you've got covariance of x comma y. This is just again something for you to just know. So the covariance can be expressed as in this manner: the expectation of xy minus the expectation of x times the expectation of y. So of course, by looking at this, you can see why these two formulas are actually quite related in this case, because if x is y, then you come up with the formula for the variance above. So that's essentially the idea here. So now that we're done with this, we can finally move on to the most important bit. So here we're gonna start talking about, okay, can we move on to the next page? Okay, so we're gonna start talking about Bayesian probabilities, right? And this is an important topic now, because it's gonna be forming the basis of most of the material we're gonna explore in statistical machine learning. So one thing we can look at is there are two views that we have, two notions when expressing probabilities. The one that we are already familiar with is called the classical or frequentist view, right? So we've got the classical and the frequentist view. So this view is essentially what we are familiar with when we think of, okay, let's give an example. Like we look at the frequencies of random repeatable events, right? Things that we sample from, like if I toss a coin 3 times and I get heads 3 times, and if I toss a coin, let's say 5 times, and I get heads like 2 out of those 5 times, then the probability of that head is 2 out of 5, something like this. So we have an experiment, we conducted multiple times, we record the number of times that we got this value for a certain random variable, and this value for that same random variable, and we express that as a probability. That is the classical frequentist view of probability in that case, right? For instance, the toss and coin example I just gave you. So your notion of probability that you're probably familiar with is what we call the classical and the frequentist view. This is also quite similar to the example that we went through last time when we were talking about picking, fruits from 2 different boxes. This was again like that same view of probability that we were looking at then. But then there's a more general view, right, of probabilities, that more general Bayesian view, I should say, in which probabilities just quantify uncertainty, right? And by quantifying this uncertainty, okay, first let me write this down. Bayesian view. So here in the Bayesian view, we're just quantifying uncertainty. That's the idea here when we look at this. Because there's certain events, right, that we cannot exactly repeat, you know, multiple times, like the simple experiments I just described before. And these events, we might have a general notion of how probable they are, but once we gain new evidence, for instance, then we need to sort of revise our initial thoughts on what those probabilities of those events may be, right? So that's the idea here. So let's actually walk through a more generalized example, right? When we're talking about this whole Bayesian probability stuff. So before we were talking about, let's say we have a data set that we express by D, right? So D is representing a data set. And then we have W, which are the weights. You can call them weights, you can call them parameters, or whatever of some model, right? Which we express using W. So why is this where is this kind of coming from, D or W? So this is back to the second lecture, right? Let's say, let me write this in red, where we said if we have some model, right, some prediction model, where we've got Y, X, parameterized by W, right, is given by W0 plus W1X plus W2X squared. This is just an example of one model that we might have, right? Which was essentially the summation from I is equal to 0 up to some value, I don't know, m, of Wi x to the power I, right? So this is essentially what we had before. We were describing that we have some kind of model like this, and then we have X, we have W, and such things. So W was what would determine, we wanted to find the parameters of W that will make this model as close as possible to the target, right? And we said we did that by computing an error, right, over W, which can be something like, let's say, the mean squared error, right, between y, x, comma, w, and let's say the target. So the mean squared error, between this and some target t. So if you don't remember what this is, please go through the second lecture of the statistical machine learning model, where we introduced what these models are, what this W is, and stuff like that. So if you think about what we're actually doing here, okay, let me expand this further. Like when we have this whole notion about probability of observing a certain data set given a certain value of W, right? This is what we call the likelihood, right? This is essentially what we call the likelihood. What is the likelihood that using my current set of W, my current values of W, that I'm going to observe this data, right? And the frequentist approach, if you really think about it, if you're familiar with machine learning, is basically trying to maximize the likelihood and stuff like that. I'm going to explain what I mean by that in a second. But first, let's, okay, you know what D is, you know what W is. Let's look at it from, Bayes' theorem's perspective. So we can say probability of W given D is equal to the probability of D given W times the probability of W over the probability of D, right? This is one way. This is how we express this expression using the Bayesian theorem. And from the last lecture, if you remember, we called this the posterior. Maybe I should write this in a different color. So we called this the posterior. We call this the prior. We call this a normalization constant. And I'm gonna express why in a second. And we just call this the likelihood, right? This is essentially what we have. These four terms. So if we just ignore this normalization constant, why are we ignoring it? Because essentially we say this is just expressed as an integral of P D given W times PW, right? So this is just normalizing all this so that the probabilities are all summing up to 1 at the end of the day. That's essentially what this is in this context, just some normalization constant. So we can actually express this as PW given D, right, is proportional to PD given W times PW, right? And then just ignore the normalization constant because we're not using this proportion thing. So what does this mean, right? This means that the posterior, right, is proportionate to the likelihood multiplied by the prior. Okay. So in case you forgot, we were saying the prior we would describe this as our initial belief on what the probability of that variable might be, and the posterior was kind of like that same probability given new evidence. That's essentially what it was. So for example, in that picking fruits from a box towards the end of the previous lecture, again if you remember, what we were saying is that we have a probability that a box is red and the probability that a box is blue, right? So let's take for example the probability that the box is blue. We have a prior belief on what that probability is, and then we gain new evidence that the fruit is an orange. Now what's that probability? And we call that the posterior, you know, like after we gain new evidence. So that's just a general idea of how this Bayesian probabilities are actually working. But let me actually try to compare this with something that we might already be, somewhat familiar with. So maybe I should create a new page. So again, let's go back to the frequentist view, right? Before actually writing this, let me re-express the term. So D is referring to our observations, right? These are our observations or data. And then we've got W, which is our weights or parameters. So one thing is that how is the frequentist view doing this, right? So this is probably, so if you are already familiar with some machine learning, probably you've heard about this thing, but I'm just going to express it. So we're trying to find the probability of a data set given some value of W, and then we use some kind of estimator, to find the W that actually, that actually maximizes this likelihood, I should say. So this is our likelihood, right? And then one estimator that is used in the frequentist view is called the maximum likelihood estimate. what is the maximum likelihood estimate? We try to find the W, right, that maximizes this probability. What does maximizing this probability actually mean? The probability of observing this data set given the value of W. So let's find the value of W that maximizes probability. It makes sense in that way, right, that the W is optimal under this data set that we have. So this is quite kind of one thing we do in the, under the frequentist view. So our estimator is, like a maximum likelihood estimate of this probability that we defined here, right? But one thing we should know that W here, it's a fixed parameter, right? We're not finding all possible values of W and trying to have a distribution of probability over them like we do in the Bayesian view, which I'll get into in a second. Here W is a fixed parameter. We just want to find a value of W that maximizes the likelihood of this probability here. Right? That's what we're doing in the frequentist view. And then we kind of compute the error by looking at maybe possible data sets that we can have under W. So this is kind of a technique called bootstrapping, right? Right. So what is bootstrapping? So essentially, let's say our data set, right, comprises of values x1, x2, up to xn, right? And then we're going to sample, let's say, xa. We're going to sample from this data set. So here there should be some kind of sampling. Where we sample xa, right, to take some value x1, x2 up to xt or whatever, and then we have another xb, which is taking some values, blah blah blah, and so on. All the way up to xal, which is also taking some values, right? So we have this, L sort of models, as you can say. So what we would do essentially, this can be sampling with replacement or whatever, this is the idea. So we generated this mini data sets from the data set that we have, right? And after that, we're going to find values of W by using this data sets that we created, right? So essentially we have multiple models in this sense. So we use this data set to come with some values of W, use this data set to come some value of W, use this data set to come some values of W. Then we combine the output to see how these models actually vary with each other, compute whatever like estimates we want to make from this. But if you look at it, we are sampling across, we're looking at different distributions of the data sets in order to compute our error bars. So we're looking at different distribution of data sets to compute our error bars, right? This is essentially what we're doing. We're looking at the different distributions of the data sets. So this is kind of still in line with what we call the frequentist view, essentially, right? So this is what we're doing, just maximizing this likelihood function. But now let's turn and look at the Bayesian view, right? So we saw that in the frequentist view, the most important thing was this likelihood. This likelihood is giving us probability of the data set we observed given the weight, essentially, right? because that's something that we can compute and we can maximize or whatever. But now, here in the Bayesian view, we start computing the probability of W given D, which is essentially probability of D given W times the probability of W given probability of D. So let's just ignore the normalization constant for now. So let's look at this. This is our prior, right? This is our belief that the weights of the probability distribution, that the weights are actually following, right? This is our initial belief. But then now we have this likelihood function, right? We have this likelihood function that comes in and says, okay, we actually look at our observations, right? And what the probabilities of those observations given some value of W, right? This is what this likelihood is. And what this likelihood does, it only helps us update our prior to become our posterior, right? This is the difference in the Bayesian view. We're no longer just maximizing this likelihood and stuff like that. We're multiplying it by our initial belief, right? This is kind of like, our initial belief on what the value of W is. That's what the prior is indicating in this case. And then we multiply it by the likelihood, and then we get a posterior. But now, this posterior, as you can see, it's not just a single value of W, is it? This is a probability distribution. Over W, right? So this is a probability distribution over W. So we're not, unlike in the frequentist view where we're just trying to maximize the likelihood of, where is it, this function here, and getting one fixed W weight vector or matrix, whatever it is. Here we're actually returning a probability distribution, like what is the probability of having this W, right, compared to having this other W. So W becomes a distribution given the data set that we've observed, essentially. So where in the frequentist view we're getting W as a fixed parameter, here we're getting W as a probability distribution. This will make a lot more sense when we actually go through some examples and how we actually utilizing this. But it's very important to essentially understand what this view is, how it's different, I guess, from the frequentist view. So the advantage here, if we use a ridiculous example, for instance, like take a coin toss, for instance. If you toss a coin, let's say 3 times, right? You don't have enough experiments for doing this. So you toss a coin 3 times, and so toss a coin 3 times, and then 3 out of 3 times you get a head, and 0 out of 3 times you get a tails, right? So if this happens, according to the frequentist view, the probability of getting a heads is 1, right? And the probability of getting a tails is 0, assuming this is a fair coin, right? Of course, in this case, this only happened because we don't have enough experiments to get the true probability. But if you think about it, in a real setting, when we sample data, right, we don't always have like lots of data to make the perfect model, for instance, right? So when we say that, okay, we are tossing a fair coin 3 times, 3 out of 3 times it has, or 3 times it tails, the frequentist approach of just maximizing the likelihood over here, it's just, okay, Essentially, it's just telling us, in this case, I forget what I said just now, but it's telling us that the probability of getting heads is 1, the probability of tails is 0, which is kind of ridiculous in this case, right? Um, but if we look at the Bayesian view, and if we have a good prior, right? So when we actually look at this likelihood function, we're actually multiplying it by our prior. So the result will not be as extreme as this, right? This is the idea, this is the advantages of having a prior. But of course, there's a lot of debate that goes on as to uh, how do you actually, is this approach really good? Because how do you decide on what prior you should use? Sometimes people choose a prior out of mathematical convenience, rather than reflecting what you truly believe the prior beliefs to be. So of course, if you don't choose your prior correctly, the probability, the model is actually just going to get worse. um, so that is the idea. But since we are exploring um, Bayesian machine learning, we are going to be focusing on the Bayesian view, as is the book that we're also using in this case. So essentially, that's what we're going to be doing. So I hope this gave you some idea or some, notion on what this Bayesian view is, how it differs from the classical view, um, and how in what situations it's actually an advantage, I should say. So with that, I'm going to end this lecture. Thank you.